Okay, so we are deleting a value from the binary search tree. So let's suppose I have to delete this 10. So this is first case where if I am going to delete this. So what will happen? This is a one case where the node has no child. When node has no child, then the parent of this will be taking it as null. So here 12 of left will be null in that case. So in that case also we need to see whether this is a left child or right child. Based on that, you need to do left or right null for the for its parent. Now, if I want to delete a node which has just one child, so you can see this 12. If I want to delete this 12, okay, so 12 has just one child, right? So what will do? Since 12 is the right child of its parent, so always you have to keep the track of parent. So 12 is right child of its parent. So left of for 12 will be connected to the right of this uh, its parent, right? So 12 will be removed from here and 10 will be connected to right of it. Okay, like this it will be connected and this connection will be broken, right? Now the main thing comes when you want to delete a child who has both child, right? So let's say if I want to delete this 30, if I want to delete this I am going to delete this 30, right? So 30 has both child, left child and right child. So now in this case what we discussed in last class, either we need to replace this element. It can be replaced by two element, either the rightmost child of left subtree or leftmost child of right subtree. So either we can replace it with 29 or we can replace it with 40. In both case, whatever we do, this this situation will be supporting. So anything we have to do. So um, just give me a second.
Yeah.
We are going to replace this. I means the biggest element of left subtree or the smallest element of right subtree. So for that, what we did was here in our code, what we were trying to make this min val node. This min val node will find the smallest element of right subtree. You can make it your own version of where you can try finding the maximum value of that left subtree, the biggest value of left subtree. You can try finding that, and that can also be the way to implement this. Okay, so now we have to make this function which will tell that how to find the biggest element of sorry, smallest element of right subtree. Okay, so let's say we'll make this min val node here itself. We'll make a different function for this. Okay, so here we'll define default min val node. Okay, and in this min val node, what we have to find is we have to find this node value. We have to accept this node value. This node value will be will take current is equal to node. And now what we have to do is, so here what I am passing is the right subtree. So the right of ND. So ND is the node which has to be deleted. So right of that I am passing over here. Okay. Now I have taken this over here, and now our job is to find the smallest element. Okay. So we'll see where we'll get the smallest element.
At the root?
at the not root. Smallest root element cannot be the smallest element. The leftmost element will be the smallest element in the right subtree.
Okay, yeah.
Okay, so we have to go, we have to move till we find the left is equal to null. Okay, so while um current while current dot left is not none. Okay, so we have to do is current is equal to current dot left. So till we don't find the left of this is none, we'll keep on moving towards the right left side, right? So when we'll find that now the left value is null, right? There is nothing on this, then we'll return this current. Okay, we'll just return this current. So this will return um this will return this will return the smallest element of the left subtree. In the same way, you can make it for the left also. So here I can write it as define max val node, and here also I'll take this node, and here I'll take this current is equal to node. So now when if I have to find when I have to find the biggest element from the left subtree, then what we have to do, we have to move till it reaches the most right, while right is not none. Okay, so when this will be doing so we'll do current is equal to current dot right, and then return and return current. Okay, so you can use either this or this, anything you can use, and you can execute this. So now I'll execute all these functions, and let's see how these things are working. So this is um, mm, 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 mm. Okay, sorry, elif. Okay, so I'll execute this. So this is executed. I'll execute this. I'll execute this as well. Then where we have to do. Okay, so now we'll create the tree for this. So let us create the tree first of all. I'll take some more elements over here so that let's say I'm taking this value as root value. I am taking as 30. In the left, I am taking 10. In the right, I am taking um 50. Then I am giving let's say 6, and here I am giving um 90. Okay, and I'll create some more. Sorry. So here this let's say this value is 40, and this value is 25, and this value is um 29. Okay, so let's see how this tree is getting created. So I'll try to create in same way again. So I'll take at the root, I'll take 15. Then at the left, I am taking this 8, and at the right, I am taking 30. Then I am taking 4 over here. Then I am taking 12, and then I am taking 10 over here. Then at the right, it will be taking 30, and here it will take 22. I'll add some more values over here. So after 22, there is 45. There is 45. Then 18, 29. This is 18, and then 29 I am taking. And then I am taking 40 and 48. 40 and 48 I am taking. Okay. So when I'll execute this, it will create the entire tree in in the way we have created over here. So I need BST we have not called. Yeah, I am calling I need BST. So this will not be there. Yes. So yes, I'll execute this now. So I'm running this. So for root node, it is created, and pre-order. Okay, I have not executed this part. So this is done, and this is done. Okay, now I'll execute this. So root node is created with 15. So now you can see here, it has created this order. Where is okay in order, in order. I'll execute this. So here now in order value will be this. This is in order, and this is post order is also not executed. Post order, post order. Okay, I'll execute this. So now our tree is created. You can see this 15 is at a starting. Here 15 it is at last. Okay. Now what I am going to do is I am going to delete a node. Okay. So let's say I am going to delete a node from this. So what I'll be deleting? Let's say um, here with search, I'll be doing this. First of all, search I'll be implementing, and after that we'll be deleting. So we'll ask del element del val. I will take integer input, enter the number to be deleted. Okay, and here it will get that number, and now here I'll call this delete bst. Okay, in delete underscore bst will call, and here will pass values of right nd. So nd is our uh, root node is the nd, and then del val. So root will pass and will pass del underscore val. Okay, after this, what I'll do is in this I'll be executing this in order. Root pre-order and post order. So I need to do this because I have not still I have not made the structure. So you need to make a structure to demonstrate all these things properly. Okay.
Okay.
So just make you have to make this. I'm not going to repeat that. When you will be implementing, you need to practice that. Okay, once I have just told you about the structure, rest the implementation you have to do. Okay, I can make it by myself also, but then you will not practice that. Understood?
Yeah.
Um, okay, okay. Now we'll execute this. So let's execute this. The number to be deleted. Let's say here our tree is this, and here I am going to delete this. Let's say 10 I am going to delete. Okay. So when I'll delete 10, nothing will happen. So only this 10 will be disappeared from here. Okay. From here, it will be means at different places it is there. So let's say I'm deleting just 10, right? So what happened? Delete. What is the function name? Delete underscore bst I have taken. Okay. Sorry. Delete underscore bst. Delete underscore bst. And this is again underscore bs. Let's execute this, and I'll execute this now. So let's suppose I'm 19. Was there any 19? No, 19 is not there. 10. Okay, so print, print 10 I'm deleting. You can see here now 10 is not there anywhere in this list. Okay, 10 is,
Yeah.
10 is removed from this list. Okay. Now let's say I delete this 15. So when I'll delete this 15, what will happen? When I delete 15, as per our logic, the 18 should be the root node. Okay. So let's say I'm deleting this 15. Okay. So okay. So you can see now 18 is the in pre-order you get the root at the first, and in post-order you get root at the last. So you can see here in pre-order 18 is the first, and here in post-order 18 is the last. So now 18 is your root. Okay.
Okay.
Okay, so everything is working fine now. Now it's on you that how you can you need to make this menu wise. So what I'm doing is, since you have not done the task, you need to share your screen and you need to make that menu wise now. Okay.
Okay.
So I'm just sharing this entire program code with you. You just make the entire code for to arrange this, so that you can arrange this in menu wise, where at every step you need to ask that what to insert, what or whether to insert or whether to delete. Okay.
Okay.
Okay, so you can share your screen and start making that.
Okay.
Share your screen.
Yeah, I'm opening this.
Have you joined with the mobile?
No, I'm opening the code.
Okay, no issues.